Hi, this is Wendy Lightheart, and in this video we are going to learn how to graph quadratic functions. The graph of a quadratic function is called a parabola. A parabola may be opening upward like the two parabolas that you see here on the left, or opening downward like the parabola that you see here on the right. A parabola is always exactly symmetric about a vertical line that goes through its vertex. This line is called the axis or line of symmetry. So here in all three of these graphs, the red point on the parabola is the vertex. So it's either going to be the lowest point on the graph or the highest point on the graph, depending on if it's opening upward or opening downward. Okay, let's go through the steps of how to graph a quadratic function in the form of f of x equals ax squared plus bx plus c, or it might be written as y equals ax squared plus bx plus c. So first we want to determine whether the parabola is opening upward or downward, and this has to do with the value of a, the coefficient on x squared. So if a is positive, this tells you the parabola will be opening upward. If the a is negative, then it will be opening downward. Then you will find the vertex of the parabola. And we'll see in the next slide how to find the vertex of the parabola when your function is in this form. The third step is to find any x-intercepts by replacing the f of x, or the y if you have a y instead, with 0, and then solving that resulting quadratic equation for x. So exactly the same way that we find the x-intercepts of a line, where you would replace the y with 0 and solve for x. Finding the y-intercept is also the same as we do for finding the y-intercept of a line. We replace the x with 0, and then we evaluate that, and this will give us the y-intercept. And then the last step is to plot all those points that you found. So plot the intercepts, the vertex, and then we'll also look for additional points that we can plot that will help us to draw the nice smooth curve that needs to be shaped like a parabola. Okay, so finding the vertex of a parabola with an equation of the form of either f of x equals ax squared plus bx plus c, or y equals ax squared plus bx plus c. So if your function is in this form, then there's a formula for finding the x-coordinate of the vertex. So the vertex is going to be the point negative b over 2a, and then f of negative b over 2a. So in other words, the x-coordinate of the vertex is the value negative b over 2a. So you're just using those coefficients. The coefficient on the x is your b, the coefficient on the x squared is your a. Plug them into this formula, negative b over 2a, and simplify, and that will give you the x-coordinate. And then the y-coordinate can be found by plugging that value into the function in place of x. So let's do an example. We're going to graph the function f of x equals x squared minus 6x plus 4. So the first thing we're going to do is look at whether it's opening upward or downward. Well, notice here that the a is 1, which is a positive number. So this tells us that the parabola is opening upward. Next, we'll find the vertex. So we start by finding the x-coordinate of the vertex using that formula again, negative b over 2a. So that will be equal to negative, and then negative 6 goes in for b, and then divided by 2 times 1 goes in for a, which simplifies to negative 3, which simplifies to 3. So 3 is going to be our x-coordinate of the vertex. Then we find the y-coordinate by plugging in that value into the function. So the y is going to be whatever f of 3 is, which means we go into the function, replace all the x's with 3. So this will give us 9 minus 18 plus 4, and that simplifies to negative 5. So the vertex is the point 3, negative 5. So far we have two pieces of information to help us graph our parabola. And next we're going to find the x-intercepts. So remember, we do this by replacing the f of x with 0, and then we solve that resulting equation. Now when we go to solve this equation, the first thing you should try is factoring. If it easily factors, that's always the easiest method. You could try factoring this, but of course it does not factor. So then the next easiest method, I think, if it's in this form, would be the quadratic formula. So you might pause for a second and write down the quadratic formula and plug in all the values, and then compare it to what I'm going to show here next. So when you plug the values of a, b, and c into the quadratic formula, you should get this: negative 6 plus or minus negative 6 squared minus 4 times 1 times 4 all over 2 times 1. So if we simplify that up a little bit, negative 6 would simplify to 6. And then if you simplify everything underneath the square root sign, that will simplify to a positive 20. And then that's all divided by 2. Now we could simplify this a little bit more if we wanted simplified radical form, but because we're using this to find the x-intercepts, we really just need to find the decimal estimations of these two values that we're getting here. So plugging into your calculator, 6 minus square root of 20 all over 2 would give you approximately 0.8. And then plugging in your calculator, 6 plus square root of 20 all over 2 should give you about 5.2. So our x-intercepts are the points 0.80 and 5.20. Okay, so now let's find the y-intercept. And remember that we find the y-intercept by replacing all the x's with 0. So when we do that, we'll have 0 squared minus 6 times 0 is 0, plus 4, that's going to give us a 4. So that tells us the y-intercept is the point 0, 4. Okay, so lastly, we'll plot all these points that we've found so far, and then we'll use the symmetry to find an additional point or more. So here's our grid, and remember, first we found the vertex 3, negative 5. So if we plot that on our grid here, we'll go right 3 and down 5. Then we found the x-intercepts next, so we're going to have to estimate where these go. So 0.8 is going to be not quite at x equals 1, so just shy of that first grid line there. And then 5.2 will be just past the 5, just barely past 5. So we estimate those points there. Those are our x-intercepts. Then we found the y-intercept to be the point 0, 4, so we go up 4 on the y-axis and plot a point there. And then remember that the parabola is going to be exactly symmetric about the axis of symmetry. And the axis of symmetry always goes through the vertex. So that's going to be the vertical line we would call x equals 3. That's the equation of that line. Now because of the symmetry here, notice that the two x-intercepts, see how they're equally spaced on either side of the axis of symmetry? Well, we're going to find the mirror image of the y-intercept the same way. So notice that the y-intercept is 3 units to the left of that axis of symmetry. So staying on that y equals 4 grid line there, we're going to go 3 units to the right of that axis of symmetry and plot a point there. Okay, so that gives us another point to help us to draw the nice smooth curve. So we'll fill that in with a nice smooth curve. We put arrowheads on the ends to indicate that these will go on forever in both directions, and that is our parabola. And remember, we predicted that it would be opening upward because our a value was positive, and sure enough, it's opening upward. Okay, so here's another example where we want to use the graph of our function to find its domain and range. So remember that the domain is the set of all x values that can be plugged into the formula. So if you notice that these arrows on the end of the parabolas, those are important because we wanted to indicate that it's going to keep on going up forever and ever. And notice that the parabola is getting wider and wider and wider as we go go further out. So really, it can keep getting wider forever. So in other words, the x values from the axis of symmetry all the way to negative infinity, any of those x values we could plug into the function, and same goes for all the values to the right of the axis of symmetry. And if you think about it, this should make sense. If you go and look at the function, there really is no x value that I would not be able to plug into the function and get a number, get a result. So the domain is really all real numbers, which we would write as the interval notation from negative infinity to infinity. Now the range of a function, of this function, notice that, or remember that the range is all values of y that are possible. So if you look at the parabola, notice that the parabola does not exist below the y equals -5 line, right? There's no parabola down there. So we can say that the range starts at -5, right there at the vertex, and then it's going to go upward. So all the possible y's start from -5 and then go up to infinity. Because again, these arrows on the ends of our parabola indicate that it goes on forever in that direction. So our range is going to be all real numbers from -5 to infinity. Alright, so now let's look at graphing a quadratic function that's written in a different way. And this is often called vertex form. So if you see a function that's written in the form of f of x equals some number a times x minus h squared plus k, we can call this vertex form. And if that's the case, it's written in that form, then the a really is the same as before. If it's positive, that tells us the parabola is opening upward. If it's negative, that tells us it's opening downward. Now the nice thing about this form, it's called vertex form because when it's written in this form, you can actually see the vertex. You don't have to do any kind of calculation or use a formula to find the vertex. You can simply look at the function in the way it's written and see the vertex, because the vertex is going to be the point hk. So you should be able to look at the formula and just see those numbers in the equation itself. Then we would find the x-intercepts in the very same way we did before. We would replace the f of x with 0 and then solve that equation. And to find the y-intercept, we do the same thing as before. We replace all the x's with 0 and solve. And then we plot all the intercepts we found, plus the vertex, plus any additional points that we can find, for example, using the symmetry of the parabola. And then we connect these points with a smooth curve, which is always going to be shaped like a parabola. So let's look at this function here. We're going to graph the function f of x equals -2 times x plus 5 squared minus 6. So when you see a binomial with x right there being squared in your function there, that's a good clue that this is written in vertex form. So the first thing we need to do is to find the values of a, h, and k, because remember the a is going to tell us whether it's opening upward or downward, and the h and k will be the x and y coordinates of our vertex. So here's the vertex form again. So we need to rewrite this into that form, because notice that we don't have x minus something inside the parentheses here. We have x plus 5. So we're going to rewrite that as subtraction so we can see the h. And then instead of having a plus a number at the end, we have -6. So we're also going to rewrite that subtraction as addition so we can see what the k really is. So here's what it looks like when we rewrite this, the addition, x plus 5, as subtraction. That's really the same as x minus -5, right? That really means the same thing, but now it's written as subtraction. So we can see what the h is. And then writing -6 would be the same as writing plus -6, just rewriting it as addition. So now we can see that the a is -2, the h is -5, and the k is negative 6. Okay, can you see that? All right, so now what does this tell us? Well, since the a is negative 2, that's a negative number, so we know that the parabola is opening downward. And then we know that the vertex is going to be the point negative 5, negative 6, since the vertex is always the point hk when it's written in this form. So there we have two pieces of information to graph our parabola. So now we will find the x-intercepts by plugging in place of f of x, we'll plug in 0. And then we'll solve this equation. Now this equation, notice, has a binomial squared here, so whenever you see that, remember that it's easiest to solve that with the square root property, because we can isolate that binomial squared and then square root both sides and solve it from there. So that's what we're going to do here. I'm going to first isolate that perfect square. I'm going to do that by adding 2 times x plus 5 squared to both sides just to get that positive. Then I divide both sides by 2, again to isolate that perfect square. And now I'm ready to square root both sides using the square root property. So that would give me x plus 5 on the left and plus or minus the square root of negative 3 on the right. Now when we simplify this radical, if we take the square root of negative 3, remember that that's really an imaginary number. So we pull that negative sign out, it becomes an I. And we can subtract 5 from both sides to isolate the x. But really you should be able to tell, a couple steps back, that we're actually going to get an imaginary or complex number solutions. So what that tells us is that there are no real solutions to this equation, which tells us that there are no x-intercepts. So whenever you get complex solutions like we have here, that tells you that there are no x-intercepts. Alright, so now we're going to find the y-intercept by replacing x with 0. So this one's not quite as easy as the other form. If we place the x with 0, we're going to have to follow the order of operations here by adding 0 plus 5 first to get 5, and then we'll square the 5 to get 25, and then multiplying negative 2 times 25 gives us negative 50, and then subtract 6 last to get negative 56. So our parabola is crossing the y-axis at negative 56. So that point is going to be the point 0, negative 56. So now we're going to plot all the points we've found so far. And so remember that the vertex we found earlier was the point negative 5, negative 6. So we're going to go left 5 units from the origin and down 6. And remember, there were no x-intercepts. So if you think about it, that should make sense here because we're already below the x-axis and our vertex is there. And we know, since the a is negative, that it's opening downward. So if it's opening downward from the vertex, it's not going to be able to cross the x-axis. So that should make perfect sense. So we don't have any x-intercepts, but we can plot the y-intercept, which remember is the point 0, negative 56. So we go down 56 units on the y-axis, plot a point there. And then we'll use that symmetry. Remember, the axis of symmetry always goes through the vertex, so it's going to be the vertical line, which has the equation x equals negative 5. And notice the y-intercept is 5 units to the right of that axis of symmetry, so there must be another point that's 5 units to the left of that axis of symmetry, having the same y coordinate. And so that's enough points. You could plot in some or plug in some x values to find more points if you want to help you draw a nice smooth curve. But I'm just going to use these 3 points here. I know it's supposed to be curved, so I'm draw a nice smooth curve through the vertex and going through those 2 points I have here, and that is my parabola. Okay, so we've looked at the 2 main forms we're going to be graphing when graphing quadratic functions, but they'll always look like the shape here with a parabola either opening upward or downward. All right, so you're going to be doing lots of graphing of these quadratic functions now that you have several methods for solving quadratic equations. So have fun.